Right, let's look at some examples of using the ideal gas law. So we're going to do it in two different ways because there are two main ways that we apply the ideal gas law. One of them is when we're not too worried about how many molecules are in the gas. So all we know is that we have the same number of molecules in the two states, but we don't really have to do any absolute calculations about the number of moles of molecules. So we can use the fact that nR is equal to a constant, which means that PV over T is equal to a constant. So if we have two states, 1 and 2, for example, then in the first state we would get P1 V1 over T1, which would equal these values in the second state, which is P2 V2 over T2. So that's a bit abstract, but let's do an example. So if we have a gas which is initially at temperature T and pressure P and volume V, and then we're compressing it, and we might be adding some heat or take away some heat along the way, but that doesn't matter. We're compressing it and changing things about this gas until its temperature is 3T and its pressure is 9P. So the temperature of this gas has tripled and the pressure has become 9 times what it was before. And we need to calculate the new volume of this gas. So we don't really have any values at all, which is why it's very useful to use this version of the formula. So we've got the two states. Instead of calling them 1 and 2, let's call them old and new, just to make sure that we don't get things confused. So P old V old over T old is going to have to equal P new V new over T new, because we're not changing the amount of gas, so PV over T is always the same value. Alright, let's put our values in. So P old is just P, V old is just V, and T old is just T. So that was simple. On the other side, it's going to be a little bit more complicated because we don't have just PV and T. P new is 9P, so 9 times what we had before. V new, we don't know, that's what we want to calculate, so we'll just call it V new. And the new temperature is 3T. So we write that all out. And we can cancel the P and the T because they appear on both sides. So we get rid of P and we get rid of T. And now we can rearrange to get that V new is equal to 3/9 of the original volume, which is the same as 1/3 of the original volume. Sorry, you probably can't see that, so I'll write it up here. Okay, so let's look at the other way that we can use PV equals nRT. And in this example, we're going to make use of the fact that N appears. So N is number of moles. So if we wanted to find out how many molecules of air there are in this empty jar, so if I open the lid, I'll let some air in, and then I close the lid, and we want to know how many molecules of air are trapped inside this jar at this moment. So we're going to need some measurements, and we're going to need the formula PV equals nRT. So the measurements we're going to need is, first of all, the volume of the jar we're going to need. And we're going to say that this is approximately a cylinder. And for a cylinder, we need to calculate the area of the cross-section, which would be a circle, and we also need the height. So we're going to measure the cross-section, which is about 7 centimeters. So that means that the radius is about 3.5 centimeters. And we measure the height, and it's about 9 centimeters. And we're also going to need to know something about the pressure and temperature. And atmospheric pressure is about 101 kilopascals. So we'll just assume it's 101 kilopascals. And the temperature, it's quite a warm day today, so let's say it's 25 degrees Celsius, which in kelvins is 298. So remember that we always have to use kelvins when we're using the ideal gas law. You can't just use Celsius. And that applies also when we use the PV over T version. So even there you're going to have to convert it into Kelvin. But for now, we're going to plug all of our numbers into the formula. Actually, first we're going to need to calculate the volume of the cylinder. So, as I said, it's the cross-sectional area, which is a circle, times the height. And that means that we've got pi times, I'm going to convert these measurements into meters, because that way we don't have to do that at the end. So we'll do pi times 0.035 squared, because that's 3.5 centimeters. And we multiply that by our 9 centimeters, which is 0.09 meters. And we put that in our calculator, and we get that it's 3.46 times 10 to the minus 4 meters cubed. Now we actually have all the values that we need to calculate n. So write down that n is PV over RT, just rearranging the ideal gas law. And then we put all of our values in. Remember that it's kilopascals, so kilo is 1000. So for pressure, we're going to have to write 101 times 10 to the power 3, or times 1000, to get it into pascals. And then the volume we just had, 3.46 times 10 to the minus 4. And in the denominator we got R, which was 8.31, and then temperature, which is 298. So we put all of this into the calculator, and we get 0.0141 moles. So because we wanted to know how many molecules there are rather than how many moles, we're going to have to convert that into how many molecules by multiplying by how many molecules there are in a mole. So we're multiplying it by the Avogadro constant. And when we do that, we get that we have 8.5 times 10 to the power 21 molecules. Is that more than you expected in this jar? So it's not that big, but still there's 8.5 times 10 to the power 21 molecules. That's quite a big number to imagine, isn't it? So we got that many molecules just floating around in here, just because there's air in there.